welcome to Jacob. He has been, at least last year at Troopers, so some of you may know him. He's given a workshop on Monday. And if you remember last year's keynote from the second one, from Sergey, the younger brother, he made a strong point that a different, say, approach, or let's say, I could say strategy, approach is probably the right term, to development might be needed to tackle the upcoming challenges. The LangSec initiative, it's gaining ground. I'm happy it does. We have been trying as EW to add to traction, and one of the things is Jacob will lay out how to integrate a LangSec. There he is. Actually, I was just talking to give him a chance to be here when Jacob starts, which is now. Okay, Jacob.
All right, thank you. Thank you all. My name is Jacob. I'm talking about integrating LangSec fundamentals and principles into your software development lifecycle, your SDLC. Compared to the red teaming talk, I very much thank you all for coming. I'm especially pleased because I'm competing with Felix, who's going to be talking about exploitation and vulnerabilities. But remember, exploits can be patched. LangSec is forever. And I just found a perfect 007 themed slide for that. So real quick, who am I? So I work in Denver, Colorado as a security researcher for a small company called AIS. Most of my work is either in LangSec or in virtualization, SMM, or BIOS security. I'm one of the LangSec co-conspirators, not cultists. I've been corrected. And I will see you all at the run tomorrow, right? Bright and early at 7 a.m., I hope. So, excellent. The cat, by the way, is a manual cat, which is very privacy conscious. It's very hard to see them in the wild, so it's a very fitting animal to be the mascot for LangSec. So we'll talk about kind of why we're here and why you guys are here. Talk some background, some programming conventions that are out there and being used in software development shops right now, and how they map back to LangSec. And then talk about, for either developer managers, how they can start enforcing some of these conventions and how they can augment their SDLC, and then some conclusions as well. The overall problem is there's kind of a lack of metrics in security and software development to understand exactly what makes software more secure and less secure. So typically development is very much based on tradition. It's either the school of thought that your professor or your instructor taught, and they were doing it because that's the way that they've always done it. And then you have kind of these cults. So you only need to mention someone that Emacs is better than Vim, which it is, by the way. And you will find who is in your cult and who is in another cult. So because we don't really have a way to be able to look at software and say, this software is 90 secure versus this software is 70 secure, we're kind of doing it kind of hand-waving through metrics. So a lot of times you'll see programs at DARPA that are trying to measure the effectiveness of their cybersecurity, and what they'll do is they'll just try to measure by cost of red teaming. Like it took a red team twice as many hours to do it after I've implemented this control, and it was only a few hours before. And also software is becoming more and more diverse, it's more and more common, and it's all over the place. And secure composition is a very, very hard problem. You can have a very locked down system with good application security, and then someone plugs in a light bulb with a GSM modem in it. It also has, connected to the cloud, so you can sync your iTunes library to the light and the theme and make a little dance party, and then there you go. So because of this, we have some challenges in software security. So last year's keynote, my favorite things, showed some of the theoretical underpinnings of cyber insecurity, which is kind of a way to talk about LangSec, which is language theoretic security, which uses basically computational complexity to try to show why vulnerabilities exist and how you might be able to address or reduce them. So What you're looking for with LangSec is these weird machines that crop up, which are typically where exploits play. And then exploits are thus proofs of insecurity. So I think Felix said you can't argue with a root shell. I mean, that's your proof right there. What I still saw was missing after that talk was a recipe book to be able to translate words like the Chomsky hierarchy, recursively enumerable languages into something that I can add to my SDLC and tell my developers, say, hey, do this, do that, and let me check that you're actually doing it. So those are my goals. So I would hope that you all, when you leave, understand how LangSec kind of applies to software security across the board. And have some framework, some tools, some concrete and some theoretical to how you'd be able to translate that into improving the state of security in actual software that's being shipped, which is our goal to make the world a safer place on the Trooper's Crest. So for developers in the crowd, recognizing constructs that are dangerous, avoiding defect-prone semantics, and then for project managers, figuring out how you can basically audit to make sure that people are compliant, maybe. And also to be able to sell to your stakeholders in the business that there are some benefits of using this that are not just for security but also for cost and performance. And by reducing the defect rate, you're going to save time in QA and testing and response to bugs. So my kind of mindset for this is that bugs will happen. I mean, to err is human, right? How your SDLC is designed dictates where in that process they'll be discovered and how you'll react and how you'll be able to address that. So sooner you find the bugs, the better, right? Because that means your production defect rate goes down, which saves you costs, it improves security, and there's less putting out fires so you can focus on whatever your core business is rather than responding to showing up on the top of Wired magazine for whatnot for having a CVE published. So if you're out and you find some vulnerability in the design and architecture, so the last talk Casey talked about was basically some of these architectural flaws of application whitelisting. If they had discovered some of those about those insecure paths earlier, that would have been really trivial for them to solve it. It would have been really quick. If you're writing your code and you're starting to find vulnerabilities, I mean, sometimes Microsoft will blacklist certain unsafe like GetS or scanf. And you look at how happy these guys are, right? Because they're able to pretty easily get almost immediate response if they've made a mistake. Then you get into the dynamic testing, you get into QA and running your unit tests, and hopefully they have pretty good coverage. But again, it's hopefully. Now you're playing a little bit of a gamble. Getting a little less fun is when you get a bug reported to you by someone else. And this is now Liam Nilsson has to go out and find that bug and figure out how it kind of showed up. And now you run into more secure by composition, where you need to figure out where in all your systems that bug came from. Did you actually fix it? So the stage fright vulnerability was a great example of someone found a bug in Android. He submitted a patch. They checked the patch and said, yep, that goes against this one thing. And then as soon as they finished patching, like what is 17 million Android phones, Exodus Intel said, ha, I got you. That's actually still vulnerable. So that's not when you want to do it. And if you're really unlucky, this is the former head of the OPM in front of Congress, not looking super happy because the House Oversight Committee had hauled her in for a special session on why the entire clearance database of the United States of America had been compromised, including everyone that was in contact with someone with a clearance. So yes, that's what you don't want to do. And a lot of times breaches, people find out about breaches and security vulnerabilities by the FBI knocking on their door. Hey, we found this on some Russian server. Some fishbowl server. So a little bit of background. So the halting problem, basically it's determining if a program on a given input will terminate. So it's a pretty simple sounding property to be able to verify, right? And this is Chuck Testa. Nope, it's actually undecidable. So what is undecidable? That basically in general, undecidability means that you'll get an answer or you might just run forever trying to get an answer. So it's kind of intractable to be able to run undecidable problems in general and hope to get valid response. Computers might be able to run for a long time, but eventually the heat death of the universe will terminate all programs. So Then we talk about the undecidability cliff, which essentially complexity grows as your program gets more and more difficult or more complicated. It doesn't necessarily grow in a uniform pattern. So as the complexity increases, so too does tool verification of that. There's more test cases you need to write. If you're writing unit tests for an application, if it's a very simple application, that's quite straightforward. As it gets more and more complicated, so too does the difficulty of that verification. And then once you hit kind of Turing completeness for your software, you've fallen off this verification cliff. So,
what do you mean by Turing completeness?
So this is once your program has started to be able to parse the grammars that represent, that are complex enough to require Turing completeness. So typically you have unbounded or uncountable specifications. So for example, the PDF specification, they have the ability to have a length field that references another length field, and then that length field could then reference back to the original one. And so the complexity for that is you could make a very small PDF file that when you open up. Yes, and so now you're going to have challenges. In 2 slides, I'll give some more concrete examples of why you'd want to verify and how the complexity of what you're parsing and what in the data you're handling with can lead to security vulnerabilities.
Yeah, but basically, an element of syntax, like say recursively nested records with nested links that must all agree, might push you over to the next complexity class. Does push you over to the next complexity class, and so the choice of your syntax may already cost you there being no effective algorithm to verify that, say, 2 parsers parse the same thing. I can go on forever.
So verification, so what is that? Basically, I say developers are not infallible. Myself even, I have a funny anecdote when I get to later about some of my code that I was writing for my demo. So you want to trust that your developers are not malicious, but you also want to verify that they're doing the right thing and they're not making small mistakes. I mean, that's kind of assumed. Car accidents happen, and you have to be able to exist in that world. So static analysis basically looks at the source code or a binary without executing that, and so that means it's static. So the problem is that sometimes runtime semantics, so indirect jumps, or if you have basically a list of function pointers for setup that change depending on how the program is run, those semantics get lost, so you're missing that gap. On the other side, when you're verifying, you could use dynamic analysis, which basically runs it in some instrumented form or in a hypervisor or whatnot, and looking through bugs that way. The problem is then you need to be able to drive execution across, basically exponentially exploding control flow graph. And so now you have problems of coverage. So these are some challenges that verification is a way that you can able to check your developers, but there are challenges associated with them. So a great example of static analysis fail was, so Mark Dowd found a vulnerability in SendMail, the crack adder vulnerability. Basically, it was a remote code execution vulnerability in address parsing. It was a while loop that was going and basically checking to make sure that, if you had carrots or whatnot in your email address, that they were matched up correctly. The problem was the semantics of what that loop was trying to do was very abstracted. It was just a while one with a break later down and some increments and decrements. So it's very difficult to figure out from a verification standpoint if it was doing what it was supposed to do. On the dynamic analysis side, typically you're going to run into NP complete problems or NP hard problems and exponential growth. So as your state space grows, you might be able to verify small program snippets or small programs. But then if you try to do it, say, give it the entire Linux kernel or the entire Adobe PDF stack, you're going to have a pretty untenable solution.
To make it you verify against predicates, not against model.
It depends on, so you can verify against, basically you could put in and annotate, this is what this program should represent, these types of mathematical transformations, or you can do things a little bit more loosely and just to say, does this program crash? Does it ever get to these error states that I've identified? Does it do something that I don't want it to do? So there's different definitions against there. You can either have a formal model, but my talk is more about how you can do that pretty straightforward, and so I'm not talking less about formally modeling your software and more about how to be able to just look for kind of implicit checks. So Hulver Flake took this crack adder and simplified it down and said, this is basically a hard problem for verification. There was a bug in this while loop, expanding, matching parentheses and carets. And then they've been working back and forth, and you'll read some literature on this if you're interested in the academic side. Basically said that they could actually detect this if they knew what they were looking for in a small, simple case. But in practice, when you have just massive amounts of software, it's very, very challenging to actually get that detection. So I mentioned parsing. So parsing, is a term that should encapsulate all boundaries or program interfaces where input is converted from one format to another. This can even be internal to an application. So the Linux kernel, for example, it gets a USB packet off of the bus, which then might have a mass storage kind of structure. And so the Linux kernel, the USB stack, will then pass it to the de-encapsulation, and then it has a SCSI command in there, which will de-encapsulate, and then it will find finally the virtual file system layer. So there's a lot of basically input happening in programs, and you need to make sure that you're understanding what that data reads, and that anything that's not against that specification, that's invalid under those specified interfaces, should be rejected. So you'll notice that there's a very happy woman who just got rejected because her invalid input was rejected. So a little bit more about some of this. So parser differentials is a great example of when you have basically the complexity of your input specification or your sloppy checks on the input specification can lead to fail. Or in the dog's face, that's kind of fine, right? So here's two examples. So in Bitcoin, it uses OpenSSL, and they use ASN1 bear encoding, which is a very, very complicated format. And they actually found that on 32-bit systems, some transactions would be rejected, whereas on 64-bit systems, they would be accepted. And so you could actually seed the blockchain with some instructions that half of all the 32-bit systems would accept and move on, and then they'd just be silently rejected by the other half. And so they're actually able to stop a split. And so they only were able to release this about a year after, and they had high enough patch coverage so that the majority of nodes on the blockchain were able to see this. So that's one example of essentially how it's very, very difficult to check that two parsers written by two different people or even running on two different systems actually consume input in the same way. An even more interesting example, in my opinion, is Ssl Certificate Parsing. There was a vulnerability, I believe Moxie Marlinspike discovered it, where essentially when you went to, say, GoDaddy and you had an SSL certificate, you could get an SSL cert for, PayPal.com, nullterminator.jacobtorrey.com. And because SSL certificates are Pascal encoded, they have the length of the string first, and null terminated does not actually terminate a Pascal string. They would grant that because that was a valid subdomain of jacobtorrey.com. Now, Mozilla, when they would read that string as a C string. So they were parsing that with a different, they were ingesting that data in a different way. And so if they went to a site that was man in the middle and pointing you to paypal.com, null terminated, jacobtorrey.com, they would say this SSL certificate is valid for paypal.com and signed by GoDaddy for paypal.com. And so this was a way that you could do SSL man in the middle with valid certificate chains because of a parser differential. And because of the specifications, the ASN1 kind of certificate formats, it was very, very difficult to find that in an automated way. It was someone finding it kind of in a exploit or a vulnerability research way.
Actually, there was quite a bit more to it, because Moxie's bug was one of the 20 bugs found by Meredith Patterson, LangSec, and Dan Kaminsky, presented at the Black Hat the same year. And it was 20 O-day of that kind, parser differentials, basically because they got bored.
So these are just some great examples, but there are many more. And if you're interested in them, come to either of us and we can give you other head points. But now you know these are bad. What can we do about them when we're developing software going forward? So MISRA is the Motor Industry Safety and Security Reliability Association. They have a C programming standard that's supposedly for safety critical code. It's used to hopefully avoid less of the Charlie Miller and Chris Volsek GPACs in the future. And a lot of the nice things about this is that it has a lot of tools, both open source and commercial, that allow you to audit your source code base against these kind of restrictions. So we'll go through some of these a little later. Another great one is NASA's Jet Propulsion Laboratory. So they have a top 10, like you must follow these 10 commandments for writing code on any safety critical stuff. So these goals, they reduce defects because typically when you have something in space, it's a lot harder to turn it off and turn it back on again. Especially when you have to worry about orbital mechanics when you need more power to start up a system because you need to heat the batteries, and that can only be done when you're facing the sun, and then if you can't just turn it off and turn it back on again unless you can do it in the right dynamic. So it's very challenging. So these goals basically make it easier to verify safety critical code. And also, there's a few of them that are for readability clarity, basically, which helps when you have attrition or new developers come on board. It makes it easier to see what that programmer was trying to do when you come across that code. So you can think of the spectrum where you have really readable code, and then you have Perl, which after about 3 or 4 days, I can't even read my own Perl code. I'm wondering what the heck I was trying to do, or even worse when you say, oh man, what idiot wrote this? And then you scroll up the top and you say it's yourself, oops. So we're going to talk about some of these conventions and how they tie back. So what I wanted to show is that we've kind of, both from LangSec, we've reached this kind of region and research that shows these are things you should do. And then we've also found basically empirical evidence of organizations that have reached kind of similar ones. We want to show that they do match, and there's actually a reason behind the badness so that people don't just try to find some other way and follow that tradition in a different path. So rule number 1 from the JPL, basically you want to make it as easy to verify control flow as possible. So go-tos are basically bad. There's a lot of debate about that. I find that just saying they're really bad to everyone, someone will find a counterexample, which, so we'll not get into that, but long jumps and recursion. Even if you have bounded recursion, you're going to run into issues now where you have cycles in your control flow graph, which makes it much more difficult to verify, similar to that PDF parser where you could have loops. And also this way you have to put more intent into your syntax. So go back to that crack adder and you're parsing an email address. Basically, if you had said, I'm just going to loop through this thing using like a for each or a for loop based on the length of that, it's a little bit easier for a verification tool to understand what you're doing because it's based on the length of that rather than a while one and it breaks on some other kind of unrelated variable. All loops should have upper bounds and iterations, so this is rule number 2. You want to be at the point, so there's some complexity class that I will just mention, I can talk more about offline, called Walther recursion. And basically you want to be in the simplicity where a program or a compiler can check to see if termination exists. So this is sub-Turing complete. This is where the halting problem is not undecidable and it is decidable. And so this is a more restricted language class. Obviously, some loops will be obviously unterminating or for the most part. And so an OS scheduling loop that only has 1,500 iterations is not very helpful if you have to turn your computer off every couple minutes or whatnot. And in those ones, you have to document and prove that they are not terminating. Again, memory map. Simplify this as much as possible. So they recommend allocating all your memory ahead of time. In that case, you don't get in a situation where you've allocated parts of your memory and then you start running into memory allocation failures, and now you need to figure out how you can kind of go from partial completion and partial state to rollback. When memory allocations are guaranteed, it's a lot easier to verify the code from that point on. So I'll talk about how you can actually check for that in your environment a little bit later. This is a really good one. So check all parameters in each function. Don't assume that there's an input sanitation that's going to go and check for all badness and everything from there is good, because you don't know if down the road your function is going to get basically put somewhere else. And if you see what return-ented programming is, essentially you're redirecting the control flow graph through an existing program, which might be a way that they could short circuit around some of those input sanitation. And so you'll see this even, the free command to free memory had a vulnerability in it where it would assume that no one would pass it the null terminator and then it would actually crash. So this is another example of just because you're at your current time and your current mindset, your code is only going to be passed safe, trusted, structured data. You want to make sure of that inside your function because you're essentially having an interface boundary there. I talked about this, about limiting your recursive pointers. Function pointers will shift these verification problems from a static to a dynamic, which makes it less likely that you'll catch it, because now you're running into code coverage. And then I talked about the PDF specification. So, strict parsing. So basically, your goal is for input data is to subject it to as much scrutiny as your compiler does, maybe except for C++ compiler, does when you're compiling code. So if you miss a semicolon that doesn't match the C or whatever language specification, the compiler will notify you of that. Currently, we do a lot of parsing in an ad hoc function where we're assuming what the person is going to give us, and we kind of compile those assumptions in. We might think of a few examples of, oh, these few things are bad, I should look out for those, but things that I haven't explicitly thought of will still be kind of implicitly allowed. And invalid input must be rejected. And a big thing, big never, is never rewrite an invalid input to try to attempt to fix it. And this is where most of the PDF vulnerabilities have been in, is that Adobe, in order to make themselves very supportive of many formats, will try to guess what the previously malformed PDF was trying to do and start rewriting it. And now you basically have a Turing machine in that kind of rewriting environment where you're reading in, changing the source code that then is going to be run later or parsed later. So using interfaces to ease interaction between teams and components, and you can use that same thing for data as well. So not just API calls, but also data formats. So founder of Amazon, he mandated that all Amazon software written will act as a service, and there will be an API, and everything will be fairly desynchronized. And that actually really helped them to become dominant in the cloud market, because everything from that way before they got into cloud services was in the mindset that we're going to be getting hit by external services, and we need to have a specification format, a way to discover that, a way to consume that, and a way to manage that. And this is basically going away from the mindset of you have a firewall that does all your sanitation of incoming packets or incoming data, and everything inside of that is safe, which the last many years has shown that that's not the case. So I'm looking for moving towards a verification-oriented paradigm. So you have object-oriented paradigms, you have functional programming. This is kind of on top of that, where basically you're trying to see how you can fit the most amount of semantic information and be the most specific you can in order to do the task at hand. So if you're looping, try to figure out how you could make the induction variables basically what it's using to calculate when that loop will bend or how that loop is related to other variables. Make that as explicit as possible. So that would be using a for with a thing. And so actually that makes your code faster, because compilers, if they can find your loop induction variable, can unroll loops better. And that's actually a performance impact. So that's a non-security benefit of writing with this mindset. You shouldn't overload your types. So like Misra C has a great way of saying that char is only for actual character data, not a small integer and not a bool and whatnot. And so that's a way that you can make it a little bit easier when you're verification. Again, if an object can't be referenced, cannot be corrupted, this is the least privilege principle for global variables, so pretty straightforward. Code is more self-documenting, it's easier to read, verification is easier, and more bugs can be discovered earlier on in the process than when you get a knock on the door from the FBI saying, hey, we found this. This is from a textbook. Basically, they did some analysis and case studies on how much it costs to fix bugs at different phases in the software development lifecycle. So, basically relative and requirements, it was very easy design and coding. And then in testing and acceptance testing, a little bit more. But then once you're running an operational environment, when you're getting these bugs coming in, that's a huge context switch, which as engineers we all know is not kind of how managers think, that you can go from right in the middle of writing code to sitting in a boring meeting right back to writing code at full productivity without any real context overhead. So this is a really simple, trivial example, but I'm hoping this will help you think about how you're writing code. So these are two semantically equivalent statements, right? So you have a variable and you're checking it against a constant. I prefer the second one, and I like having my guys write the second one. And why, you might ask? They're exactly the same. So when you implement them correctly, they're exactly the same. If you forget that second equal sign in C, what's going to happen is the first one will compile, and then it will give you unexpected results that will only be found at runtime. So this is where basically that assignment will always happen, and then it'll go through and it'll go into that loop. And now that's something you're trying to debug, a logic error. Whereas the second one will fail to compile because you can't assign a value to a constant. So this is a really trivial example, and there's a lot of other ones, but this is something that I like to see that people think. It's like, okay, if I'm going to program in such a way where I'm assuming that I might make a mistake, I want to get caught and be told about it before I get, embarrassed later. So as security, we've all heard about the least privilege principle. We talk about not running IRC as root. We always laugh when someone joins an IRC channel and their username is root at whatever, and then you give them a hard time. You don't run your browser as root typically. So basically, I like to think also as computational complexity or computational power as another form of privilege on another dimension. So right now, we're running almost everything as root. So AV relies on, well, claims they rely to make themselves work, but imagine AV working. AV relies on having more privilege. So back in the old days, they used to run in kernel. They could introspect, and they could see what was happening in user space. Then local privilege escalation became a thing, and a lot more kernel malware and kernel rootkits, and now you see McAfee Deep Defense, which is now running in a hypervisor. And now soon you're going to have SMM AV probably, so or firmware AV. So this doesn't work necessarily when you have a model like this. So right now, we might be running our browser in user space, which is fantastic. We're using sudo sh as root privileges, and you have your kernel. But you notice that almost everything here is on the more powerful side when maybe it's not necessary. So Linux, their packet filter is actually really well designed such that it is less powerful. They use that for QoS usually, and to make sure that you're not going to have some combination of packets that will never get parsed. But it's a good step, and it's more constrained on this other kind of privilege model. Crema, I'll talk about a little bit later, is basically a programming environment specifically for parsers that will always terminate. You can't write programs that are not as powerful, and that's a way that you can bound that privilege as well. So this is pretty straightforward, obviously. The more complex the program, the more bugs. And so Mudge gave a really great keynote at ShmooCon in 2011 where he showed this graph of lines of code for offense and defense. So he had a collection of basically exploits and malware from over the last 20 years or so. And the average length of code was pretty static around 280, 200, 300 lines of code. And then you look at over time, basically from the first firewall ever, the first AV, up to McAfee's HBSS, which is their enterprise DoD endpoint detection. And now we're at over 10 million lines of code. And that's probably making us less secure. But now you're also importing all these other libraries as well. With that, you're going to get less chances of detection and testing because it's going to be harder to get 100% code coverage because you just have more code to look at. You can restrict the state space. So we had a IEEE paper last year at the LangSec workshop showing that if you were able to bound your loops to a restricted complexity class, the state space that needs to be explored during verification is also restricted. And we were able to show basically the same code written in two different languages, one of which was able to get much higher coverage during dynamic analysis than the unrestricted one. And very few computations really need unbounded. I mean, the mathematical kind of concept of function application is I give you input and I get output. It's not I give you input and then nothing happens. So it's an example of this. So SDL4, the pseudo formally verified microkernel. Some of the things that NICTA, the people who did that analysis work, they kind of manually segregated all of the functionality into those that were bounded, and those were able to be very quickly verified, and those that were unbounded. All right. So now we're going to talk about how to enforce this. So this is either you can enforce it on yourself, or if you're a very mean development lead, you can enforce that on others. So all these conventions are fantastic, and I think everyone says the least privilege principle is fantastic, or don't run your software as root. But unless you can actually follow those conventions, I mean, I know I'm the first one to say that typically my password on my systems is like 4 characters or just a period and enter. Whatever I can get Linux to accept is like the weakest password, just because I don't really want to type in a really long password. So unless you can enforce those policies, it's not going to really help that much. Again, trust but verify. So what a software development lifecycle helps you do is kind of formalize these conventions and these kind of traditions into something that allows for checks of compliance. And so some of these things are code reviews, pair programming, unit and functional testing, QA obviously, commit hooks, continuous integration. There's a lot of great tools out there that you can start and just have not hugely implementing or interacting with your development cycle to be able to get more information. Again, you want to do this where you find these vulnerabilities as soon as possible, so that's how you just scale your efforts towards doing as much as you can when you're designing protocols, and then when you're implementing them, hopefully you'll already have kind of found some of the architectural problems. So again, we've kind of covered this already, but you want to try to aim to catch bugs in protocol rather than when you're on the front page of a newspaper. So when you're developing, put as much semantic mindset into your code, because that makes it easier for other people to come up and figure out what you're doing. Because if I read the Crackader, the marked out sendmail bug, it's actually very, very hard to figure out what it does, even if it was commented, just because of the way the looping constructs work. So it makes it harder for me to come up and clean up that code or work on that development effort. There are tools like CPP check that can go and look for some of these common things. They can look for MISRC violations and whatnot, and they can help warn developers. And sometimes it's just education. I mean, people come from very different backgrounds. They come from very different tradition and cults of development, and so there's a lot of heated ways. So this is a way that you can at least warn, if not measure, how your code base is doing and try to work towards something. Because you need to be able to measure before you can really improve. So I mentioned briefly Crema. Essentially, it's a compiler that targets LLVM that you can embed into anything else that LLVM can compile. It won't let you represent programs that are not bounded based on the input length, some polynomial function on top of that. Pretty familiar syntax. Is kind of like a hybrid of like Ruby or C or whatnot. And it does have some security benefits where we took software that was written in C and we re-implemented it basically line for line, and then we were able to do verification on both of those. We were able to show that we could get a lot more verification and check coverage, and this because the state space was bounded. Obviously, strict parsing. So a lot of times when you look up how to parse something, someone will say regex on Stack Overflow, and you're going to say no, because typically regex is not powerful enough to parse what we have today in terms of these designed by committee, very complicated specifications. And so then eventually someone will go on Stack Overflow, and I see this all the time, and they say, oh, just use Lex, or use Bison or Flex, which is a pretty horribly complicated and sometimes overpowered parser generator typically used when you're writing a compiler. And they're trying to basically tell some poor guy who's already asking how to parse HTML with regex on Stack Overflow, oh, just go and learn how to build a compiler, and then you can do it more formally. Those are great. There are some nice new parsers coming out. So Hammer, Nom is for Rust, which is pretty exciting. And they're designed for data parsing, so they can do really clever stuff about bit length and bit fields, and more like not just handling ASCII text, but handling binary data. And they're really helpful for this, and that's what I would recommend moving towards. And I'll show an example of something a little bit later built on Hammer called Nail, which basically allows you to take a structure and it will automatically generate both a parser and an output generator for that without really having to learn about the semantics of parsing. But you want to make sure that your format specification is as simple as you can, and use these models to kind of resist the design by convention where someone says, oh, I knew it would be really cool. If 1% of our customers ask for this, we'll add in this whole new feature. And so that's what you want to kind of avoid. You'll see this, so IPv6, a lot of work here is done on IPv6. There was a talk at DayCon a couple of years ago by some ER&W folks basically showing that the IPv6 fragmentation model is so complicated that a firewall in receiving incoming fragmented packets has two bounds. They have a QoS bound, so I have to handle these packets at a certain rate, and then also it has the I need to let only good packets through. And so you can fragment basically to create a packet chain that's too complicated to reorder and actually check, so they just kind of give up and pass it through. And so you can have a really simple SQL injection that you reorder the packets for. It won't get reordered until finally hits that server, and now you've just bypassed the firewall. So Alex Stymos has a really great talk on kind of at scale how application security is going to become the predominant security domain, just because as we start moving towards 40 gigabit per second or whatnot. He has a great analogy of a firewall has about as much time at 10 gigabit speeds to make a determination on a packet as the time it takes for a photon to bounce off of my foot and into my eye. And so that's only, I think we're talking about USB 3, the new spec that's over 100 gigabit per second. So try imagining having a firewall at that point. I mentioned briefly, so Nail, this was done by one of Sergey's students to basically automatically generate data parsers based on a grammar description. And what's really cool about this is that you can also reverse. So if you have some input format, you can then convert it to one structure, and then you can put it back out, assuming there's no ambiguities. So sometimes like C code will have white space is kind of ignored. And so if you have two tabs, and it will just get treated as white space and ignored, and when you put it back out, that white space is kind of ambiguously handled. But for the most part, it can do that. It also can automatically handle length and offset flags and CRCs as well. So if you're expecting a bit of length packet, or you're going to have one bit that says how many future packets there are, it can kind of handle that pretty automatically. It rejects invalid inputs, which is fantastic, and then also it helps reduce the risk of implementing one of these ad hoc parsers. So pretty easily, I'll tell you about. We're going to create an employee personnel database. We have the employee ID, the name, a Boolean, whether or not they're a manager, and a remote employee. And so here's that right there, where I just typed in a person, ID, name, manager, remote, and then a database, which is basically comma-separated values. I ran the nail tool against this file, and I got both parse person, parse database, gen person, gen database, and all the structures were automatically generated. So this is a really quick way that you could be able to do some of that work without having to go and do the Stack Overflow of go learn how to build a compiler. Another great tool, Clang, built into Xcode IDE, has a static analyzer that can catch a lot of things, and that really like happy guy, the kid that was really happy. You can also use this in standalone mode for other environments. And so scan build, you can basically replace the compiler name with scan build. It'll run and do static checks for common programming errors, and then scan view lets you do it. So I was writing some software in C, and I forgot to break out when I found that my malloc call returned null. So I was running it, and it said, oh, there's some bug right there. And so I was looking at it, and so basically what I did is I malloc some memory. If it's not there, I printed, oh, it returned 0, and then I forgot to actually exit, and then down here it saw that I was dereferencing it, and that was something that I was able to catch without having to execute. I just found that. And so this is just one of many classes of mistakes it will catch, and they're always adding more. Another one to do dynamic analysis is called CLE. It's one of many symbolic or concolic execution tools, which basically runs through a program to try to gain very high coverage by executing both branches whenever it reaches it, or both sides of a branch. You can find crash cases, so this is going back to your model. Basically, you're not necessarily looking for a violation of the code's logic, but you're looking for it to find crash cases. You can also use it with two pieces of code that should be semantically equivalent, say parsers, and look for those differences. So how does this work? Whenever a branch is reached, when you're running code symbolically, so you'll see here, basically we're up here, we've allocated some integers, and the constraints on that program is that this is always going to happen. And then we have here if x is less than y. If it's true, we'll just set this and we'll update the program state to that with the constraint now that x is less than y. Otherwise, we'll go down here and we'll run this and the constraints. So if we got down here to a crash, we can then solve that constraint using a solver and be able to generate an input that matches that constraint and tell you, hey, this is crashing input. It'll get you to that point. Another really fun tool, AFL, really impressive stuff. Basically, it's a compiler you can recompile your program on when you're testing, and it instruments that to help derive really high code coverage fuzzing. You can run it in distributed mode, so you can take an application and run it on Google scale. So Project Zero uses this quite a bit. And then you can provide some sample inputs. So if you have a PDF parser you're trying to scan, you download a whole bunch of random PDFs or make weird PDFs, and then it can mutate based off of that. The downside is that sometimes it can get trapped in loops if it can't kind of figure out that one rare breakout condition. So there's one more. I don't know if you guys saw this when the Pope came to the US to visit. It was really impressive, actually. He performed a pretty cool magic trick. So there's more. So these are some tools. I talked about these, and I made basically a simple repository that does a lot of stuff that people have kind of done, but maybe only alluded to on Stack Overflow. And it's basically a set of open source tools that either a statistic programming manager or even more masochistic developer can run on your code base to audit compliance. You could add it to your continuous integration suite. And it's not necessarily meant that you just won't ship code until everything is perfect, but it might mean at least you can track how you're progressing towards some goal. So there's 3 tools in there. There's one that will basically simulate memory management failures, and in the future I'm going to add some other things like threading failures if one thread gets killed by a out-of-memory killer or whatnot. Essentially, there are certain calls that you make when you're developing code that you assume always will return valid data. So if you malloc memory, you're kind of going to assume that it's always going to return information that it says you should check to make sure it's not null, because you're not guaranteed that memory. And so this you can put in a probability, and it will basically fail on all these calls at a probabilistic rate, so you can start finding vulnerabilities or bugs in your code. There's a header file you can force include with the -include on GCC or Clang that will basically poison bad looping constructs, bad or invalid dangerous functions like the getS function. And this will just basically say, all right, you can't compile this code right now until you fix these things. And then the last one will basically generate unit tests automatically for source code and then symbolically execute every single function. So what this doesn't do, well, I'll get there in a little bit. So LD preload is something on Linux that you can essentially alter the library load for that single execution. So I just LD preload libsledge.so and then whatever program, and then all these functions right here will probabilistically either return failing or succeeding. So can everyone read that? Is that big enough? All right. My nightmare is that it's like typing the password somewhere else and you're all watching. So I just wrote a really simple script just to do that, where you just run sledge run and then the name of the program. So in test, I have a really simple malloc program that basically mallocs memory, and then it null terminates it. So if I pass that string off somewhere else, if they forget to null terminate it, it's fine. So I'm going to run that program, and you'll see that sometimes it works and runs just fine. Other times you'll get segmentation faults. And this is a way that you can really quickly expose some of these really simple checks you got to do. Poison pill, this is just really straightforward. It basically, you can give it a list of constructs you don't want, and it will tell you where they are in a huge code base and forbid compilation, or you can just use it to track how many there are. So this is a really quick way just to quickly check compliance, or at least see you're moving in the right direction. The last one, CLEUnit, which is a play off of, I think, a 90s rap group called G-Unit. So CLE is a software tool I talked about already. This is just a way to provide real quick assurances that each function themselves are handling and sanitizing input, and that the function arguments are properly vetted. And then it basically combines this with Unitet methodology. And so CLE doesn't work very well like at massive scale, just because these constraints it needs to solve is going to go to an STP solver, which is NP complete, or goes back to an NP complete problem. And so by breaking it down into a unit test, you'll at least be able to all your sub-functions seem to be pretty good, but you're not going to be able to get that secure composition, the really hard problems, but at least you'll know that your little building blocks are okay. And so this you just run on a C program or a program that you're trying to compile. It'll find all the functions, it'll create test harnesses, it'll run them all through CLI. This is something you do like in a nightly build, and then it will collect all the different crashes and kind of prioritize based on what you have. There's a couple bugs in it I'm just fixing, but I'll show you real quick what that looks like. And then so here I have really straightforward. I, for some reason, don't trust the divisor, so I wrote my division, forgetting obviously to check for that. When I was writing this before, I wrote this make string as well, which turns a null terminated, and it was finding all these crashes, and then I didn't realize, I forgot that I had not typed unsigned, and it had guessed that if you put a negative value in, you're going to run issues. And so I didn't think of that. I was wondering why my code was returning the wrong number of errors until I realized that I had made a boo-boo. So now what we're going to do is we're going to run CLI unit on this test.c. You're going to see it found one error, and that error is of type division. You can go in and start like kind of digging in. You can rerun just that test. You can see all the constraints it was doing and what kind of assumptions it was making and how it got to that crash. But this is a real quick way, and CLI will run basically forever if you give it a sufficiently huge code base. So I've capped it at, I think, 3 minutes max. So this is something you can change. It's a variable in there you can set. And that's a way that you could basically really quickly go through and see if there's any like obvious gotchas that like were so obvious that I couldn't redo that when I was writing this code. So that's just a real quick way that you'd be able to augment your code base with some automatically generated unit tests, because I know writing unit tests no one loves to do. So it's all up on GitHub. All right, we've got a couple minutes for concluding remarks. So as I mentioned, Alex basically says that AppSec is eating security. You can't make these assumptions about your perimeter checking everything, and then you live inside of this nice, soft or safe environment. You have a crunchy outside and then a soft, gooey filling. So my posit on top of that is that LangSec is eating AppSec, basically, and then this is going to be what's going to start overtaking application security. A cool example of this on the network side, Google's BeyondCorp. Basically, that's their new network model where all of their internal applications, they just make facing the network. And they assume everyone is connecting from Google or from home or from wherever they are. And so they have this same threat model, not assuming that within one place there's a safe environment versus an unsafe environment. The quote I made, to err is human, to be caught at compile time divine. So that's what I'd like to see people do. Whatever languages or tooling you use, you can implement some of these ideas of trying to aim for semantic quality and verification, and you should get positive results. It's also less expensive because you're going to get less runtime bugs, and then it's also going to be faster in some cases. And this current state of security in software quality highlights the need to adjust strategy from the status quo, more moving away from tribalism to something that has some underpinnings. So, with that, are there any questions?
I have to say that every time I see talk about LangSec, I say, well, that's nice, you guys have great deep IDs, but at the end of the day, it boils down to saying, all right, just use organizers, maybe model checkers, and apply secret rules. I like what you've done, pretty much think it's a great tool, but do you think when they see one useful tool based on the LangSec principle?
I think that you're always going to have some differences between basically the fundamental theory of LangSec and understanding, but a lot of this stuff is not necessarily a tool, but it's also how you design your protocols.
I see it as complementary to model checking, because you got the guys doing formal verification.
Yes.
But it is functionality, you don't test security. And I think your idea is that you can also test security formally. And I see this as a patch to the guys doing model checking without security testing.
also it comes down to the complexity of those models and figuring out a way that you can implement or design protocols early on that don't have some of these challenges that run into model checking or any type of verification problems. And so I think that's probably the best answer is that it's going to be a cultural and educational shift. These tools are ways to kind of hit parts of these hard problems. It sounds like Sergey wants to add. Very briefly, sure.
So you see, by the time you need to apply, by the time you get around to applying your verification tools, it's too late. Basically, the first decision you make when you either pick a protocol or design one, that already may cost you basically not being able to verify down the line. You pick certain poisonous syntactic constructs. Yeah. You don't express them as such in the protocol spec, so you leave people guessing. And next thing you know, they're validating your input with something that's just woefully inadequate. And you're basically past the point in which you can verify.
If you take like the guys at Inria in France who did the verified TS implementation, so as far as I understand, they do check functionality of the model, but I don't think that they check like input. Each input is checked for.
That is correct. So the basic theoretic, if you will, if you can call it that, idea. That's right. Idea of LangSec is that basically any code is execution. Any input is a program. So it's up to you to make sure that your logic does not get in invalid state, does not get an unexpected computation, and basically you've got this one thing on which you rely, your spec and your recognizer. If you don't have that, you have nothing. And if your syntax is way too complex, why do you even trust that your recognizer is correct? Right? So just as you validate a code, right, you should validate data. But as a manager, right, there is a very simple question you can ask. In your code, can you show me where is this boundary where you have your input checked?
You have to pause on, so this is given by the user, this is given by
Correct.
Application.
Yeah, but at this point you start processing. But where is that point when you've run all of your checks? And if you see that your checks are distributed all through the code, that's plenty of space for invalid input to lead you astray, possibly. So you need that bright line. This is my recognizer. This is my processing. I do all of my recognition, and by the way, here is the syntax that I expect.
So plenty of opportunity to go on with the discussion over lunch.
So in short, some of this will have to be done at the design stage to try to minimize, because we are running into hard problems. The halting problem doesn't just go away. And so if you're trying to do this on a legacy code base, you're still going to run into some of these problems. And so I'm coming at it from a perspective of how can I kind of find ways to kind of skirt around it and minimize how long I'm waiting for my computer and try to improve the securities there. And Sergey's attention is let's start from scratch in some cases, or try to figure out how these differences in the protocol complexity then makes it more or easy or harder to do verification.
I'd love to prepare.
We have another question there. Okay, we have two. We take those two questions or comments, and after that we close the session.
Okay, thank you for giving me time. To maybe add another practical aspect. So I think one. Thank you for giving me the mic. To maybe add another practical aspect to static analysis and maybe also verification. I think one problem is that you get absolute results. So either the code is valid or is verified as being valid or not. But sometimes the rules may change. So, for example, this libOTR bug that we published last week, it was not there before we had 64-bit architectures. So all the verifiers would have said, oh, okay, this is okay, no problem. But then you change the ground rules, and then you have new bugs. So I think this would be something that should be addressed.
And so this is an example across many boundaries where you have, trying to do secure composition is probably even harder problem. And so I'm trying to basically find ways to make the building blocks easier. But again, we're making certain assumptions. So for example, a great example of this is the row hammer vulnerability, right? And so there you have code that's perfectly vulnerable or perfectly secure that is being made vulnerable by something happening in a different layer on the hardware software stack. And that's an assumption that model checkers are not checking for. They don't assume that memory writes have some other, or memory reads write to memory randomly. So again, we're having issues where secure composition is very, very challenging. And yeah, so exactly, there's a lot of issues that this does not make your code. I mean, they've shown this on the DARPA HACMS program, where they're doing formal verification of every component. Yeah, but these environments are whatever we're thinking of to test them against, whatever models we're building against, and they're secure to that. But who knows what might change down the path? Just like we're assuming that our code is being sanitized by someone else, and then we're just going to rewrite that, and now it's gone. So.
All right, hopefully this will be a quick one.
Sure.
Sometimes when I'm a big fan, by the way, of pushing bugs into compile time, right? I like writing OCaml, and I like that it tortures me because I fix stuff. But when you're teaching children to code, sometimes this is a bit of a challenge because they need things to run a little bit more easily. Now, maybe we shouldn't be doing LangSec with children, but I'm guessing Sergey might disagree. Do you have any principles on how you teach people to code with the compile, by pushing things into compile time and still make it not too torturous?
Yeah, I think that's, you'll see in education, a lot of universities are moving from what used to be a C-based course, they'll add that later in the year or later in their curriculum, and they'll start with something that's a little bit more forgiving, but gives them, less power, so to speak, like, or computational power the same, but, so that's where you're seeing, Python becoming more popular. And a lot of the hacker boot camps or the Hour of Code initiative in the US, they're using, I think, JavaScript or some pseudo JavaScript. And so, yeah, I think it's a great way, and they can write code and learn that way, but as long as they're not shipping code and shipping products, like, it's fine if someone is writing insecure code as long as they're not putting it on my device. And so that's why, so that's something that, people have to learn, right? And so starting day one, where everything that's not formally verified will not, they're not going to fail, they're going to fail CS 101. So yeah, it's just a way to iterate and get to there. Yes.
I'm willing to accept another one. Like, you have 10 seconds to express.
It's a comment, basically. So just to offer the comment that it's not all about runtime versus compile time, right? You can do a sensible design of your language barriers in a runtime compiled language, not runtime compiled, whatever, you know what I mean, interpreted language just as well. So, and I think that's the major point. To design your language interface, your language barriers at your interfaces properly. Yeah, and on that note, maybe just this last little comment to offer, that it's not only where you have serialized data in the form of byte streams that come in somewhere, but as you've said earlier, you have these interfaces in the internals of a program, and sometimes you'll have language-like structures in there, even if there's not a serialized stream going on somehow. So I think that's very interesting to see where and how you can think about these language sort of structures in the internal interfaces of programs.
Yeah, one last thing before we let you, or you go to lunch. If you look at when you compile a C++ program and you've made an error in it, it's like 50,000 lines of weird template complaining and figuring that out, versus sometimes if you do something in Python, it's like, this line right here was wrong because this variable was mistyped. And so if you start at simpler languages that still have the same kind of expressive power, I think that might be a good way to lead into there as well. So about language choice, even though they all can technically do the same thing, you probably start kids off not in Haskell or assembly, you'd start them off in something that's a little simpler. But, all right,
Thanks again, Jacob.